Conic sections can be defined by using projections of a circle, in other words by slicing it with the plane. If the plane is perpendicular to the axis of the cone, a circle is formed. If we slant it a little, an ellipse is formed. If the plane is parallel to the cone, we get a parabola. If we slant it further, we get a hyperbola. However, there is an alternative definition of a conic section. Fixing a point F and a line L, a conic section is just the locus of all points P, such that the ratio between the distance from P to F and to L is constant. Let's denote this ratio by E. For a non-circular ellipse, the value of E is between 0 and 1. For a parabola, the ratio is exactly 1. For a hyperbola, the ratio is greater than 1. For the special case of a circle, we can say E is 0 by considering the fixed line as infinitely far away. But why do these two definitions coincide? How do they have any relation to each other? Let's try to prove this. We shall start with the projective definition, so we need a cone. Then, we slice the cone at an angle. Firstly, I will inscribe a sphere inside the cone tangent to the slicing plane. The tangential point we will denote by F. We can also extend the tangential circle between the sphere and the cone into a whole plane. We will call the intersection line between the two planes L. To prove our statement, we need to pick an arbitrary point on the conic section. We will call this point P. Connect P to the origin, intersecting the tangential circle at A. We shall connect PF, and since PF and PA are both tangent to the sphere, PF is equal to PA. Project P onto the line L at D, and we see our familiar configuration. Finally, project P onto the horizontal plane at N. We want to prove that PF over PD is constant. Let's observe this configuration and zoom in. Since PN is perpendicular to the plane containing AN and D, we have that PAN and PDN are right-angled triangles. Hence, sin PAN is equal to PN over PA, and sin PDN is equal to PN over PD. Let's recall that PA equals PF as well. This gives PF over PD equals sin PDN over sin PAN. Note that PDN and PAN are just the angles of elevations of the plane and the cone respectively, which are constant regardless of the position of P on the conic section. Therefore, we've proved that E is constant for all points on the curve. We also see that E is less than 1 if and only if the angle of the plane is less than that of the cone, and that simply happens when the section is an ellipse. Furthermore, E is equal to 1 if and only if the plane and the cone are parallel, i.e. a parabola is formed. Finally, E is greater than 1 similarly when the shape formed is a hyperbola.